Hello, everyone. Good afternoon. Thank you for joining us today. Before we get started, this webinar is being recorded and we will be uploading it both to our YouTube channel and DAR website. So if you do not wish to appear in the recording, please keep your camera off. I'll introduce myself. My name is Sripriya Rengaraju. I'm a researcher exploring sustainability in the decision support framework and part of DAR Hub. For those of you who are not familiar with DARE, I'll introduce DARE a little bit. DARE is a national hub for decarbonized, adaptable, and resilient transport infrastructure, which brings UK stakeholders, including industry, government, and civic partners, to find sustainable and viable ways to get a resilient net zero transport system. So the hub is funded by EPSRC and DFT, and it comprises of a team across different universities, right from Newcastle, Cambridge, Glasgow, Hertford, and Anglia Ruskin. In today's webinar, we will be exploring on the title, Can Low Carbon Materials Drive Us Towards Sustainable Roadways? If you have any questions, please free to submit them in the Q&A or rise after the presentation. I would like to now welcome our guest speaker, Matt Wayman, who is a principal payments engineer in National Highways. He is a technical author responsible for the asphalt material specifications used on the strategic road network. He also leads on the road payment team's net zero, especially looking at asphalt innovations and sustainability objectives. Matt has spent 15 years at the Transport Research Laboratory previously, working on a range of materials and sustainability related projects, including the carbon calculator aspect. Matt is also a member of Institute of Asphalt Technology and chartered environmental scientist. So I think I have given enough introduction for our guest speaker. Now the floor is yours, Matt, and we are excited to hear from you.
Thank you very much, Sripriya. Thanks for the kind introduction and for the kind invite to speak to you today in today's lunchtime webinar. So yeah, I was given the brief to talk about low carbon materials in relation to the strategic road network, the SRN, which we look after at National Highways. And from my introduction, you probably got some idea of where I sit in the business. So I sit within what we call the Safety Engineering and Standards Directorate under the Chief Highway Engineer, and we're responsible for the design standards and specifications for road design and construction that are used on the strategic road network, which covers the motorways and the big A roads across the network, across England. There's about 7,000 kilometers of highways there. So if I just talk about, I'll give you an overview of what I'm going to talk about. So this is all from a pavements perspective. Obviously, I'm concerned with the pavement asset, and other teams in SES look after different assets. So structures, geotechnics, drainage, to name but a few. But today we're looking at the pavements, and we're going to look at a few different things across the course of about 20 minutes to half an hour. So opportunities to reduce emissions and improve sustainability in road infrastructure, some of the latest innovations that we're looking at, couple of case studies where we've actually got some of these quite recent innovations onto the network and we're trialing them, and I'll talk about the trials process. And then finally, some of the challenges that we come up against in bringing low carbon materials and other innovations to the network, and how they would become routine use in the future. So that would be, from our point of view, actually including them within a specification for road construction on the SRN. So pretty much once they go into the specification, they could be used anywhere without further question. So that's the kind of goal or end point for any innovation, and you'll see the process that by how we get there over the next few slides. So to give you a bit of context for innovation towards sustainability within national highways, so we've got strategies around net zero, and also a bit more recently resilient highways. So our plans for net zero highways were first published, well, 4 years ago, October 2021, and the image down in the bottom left here, that set the overall sort of strategy and how we would achieve net zero highways with a series of stage gates. So it's called the 2030, 40, 50 plan. So 2030 is net zero for our corporate emissions by 2030, and that's sort of that's our corporate operations. So the travel that we undertake for the company, the fuels that we use in the buildings, etc. 2040 is the target for construction and maintenance to be net zero, and then 2050 is for all the people running on the network to be net zero. So that would be sort of a full switch to alternative non-combustible fuels, basically. So electric vehicles and other powertrains by 2050, which is probably quite an ambitious target, but also it's kind of out of our, we can do things to facilitate that, but we can't, other government policy will actually bring us to that point. So on the back of the net zero plan, the initial one, we developed roadmaps for key materials, so the ones that we use in large quantities. So these were developed for the key materials that we use on the network: concrete, steel, and asphalt, being the large proportion of our overall construction and maintenance materials, and the resultant emissions from them. So that's the net zero side of things. We've also got a plan for a resilient highway network. That was released in 2022, and we report up to the government on using the annual reporting power. So we basically review our climate risks periodically and the progress that we've made to mitigating those risks, and they're reported up through annual reporting power. So those are published reports as well. And I think the ARP4 report, we've certainly done the internal part of that, and I'd imagine that will be published on government website pretty soon, so you can see the risks that we've highlighted to the network and how we're making progress to try and mitigate those. So there's a bit of context. So within further context for innovation, well, we have to do everything within our company imperatives, of which we've got 3. So safety for first and foremost. We want people to be safe on the network. We want road workers to be safe. And that's front and center of everything that we do. So we're always working for a safer network. Customers, well, there's always an element of customer service within what we do. responding to the needs of customers and their concerns about the network. And we have, for example, key performance indicators that relate to our customers. And one for pavements, for example, would be the ride quality of the network being acceptable for customers. So we're always striving for a smoother network, if you like. And then the final imperative is delivery, delivering schemes on time. Kind of sums that up, really. So do we do what we set out to do in a timely fashion and get all our ducks in a row to make that happen? So we're working in the context of these imperatives, and we're also working in the context of our license agreement. So that's the license that we have with the Department for Transport, and that sets out how we go about our business. And one key element is taking a whole life cost approach to what we do. So it's not just about delivering a scheme, it's about how long that's going to last. So there's an element of durability within using a whole life cost approach. And yeah, basically considering the asset and its whole lifetime, rather than just putting that asset there. It's about the maintenance strategy for that going forward. So that's something else that we have to keep in mind in what we do. Okay, so approaching pavement technology and how we progress that, we've got a few resources that I'll touch on in the rest of the presentation. But if you were considering putting an innovation onto the network, there's a few guidance documents that will enable you to do that. So if we were going to trial something on the network, we'd look at pilots and trials guidance to actually put that down. So that's all about following it through from the concept of the idea to actually implementing it on the network and mitigating the risks there through that process. So that is one published document. And then specifically for pavements, if we were going to take a pavement innovation, we would probably refer to this protocol for innovative paving materials. Quite a lot of them are waste derived, so it's got a bit of focus on that. But it's a very helpful document that considers all the elements of bringing along an innovation. And the key part of it is using a comparator material to compare your innovation to. So we would use an established material that we use routinely now as a base point, or like a control, if you like, and then we would look at the innovation against that comparator and how it performs against that. So either technically, environmentally, in terms of safety, for example. So that's quite a useful document for the task in hand. And then the final one, so for low carbon opportunities, they're all recorded within a register, and this is available to our supply chain, and it could be made available to anyone. You just have to request access. So you can see all the low carbon innovations that we're looking at across all assets. You can filter those down. You can also submit ideas for new innovations as well, so that we've got it on our radar. And you'll get an idea of how progressed any given innovation is. So is its technological readiness ready to go, or are we in a stage where we're trialing it? So you'd see the visibility of that. So it's also a good tool so that you don't submit the same idea as someone previously and we're already looking at it. So there's another useful resource. Okay, so how do we sort of approach innovation? We tend to take a technological readiness approach to it, and this table is an adaptation of like a standard technological readiness level approach that's been adapted for pavement materials specifically. So you can see top to bottom progressing through the TRL levels, and then an idea of what we would get to by each stage. And then these are the specific sort of pavement type considerations that we would go through. So there's a few animations. So stages 1 to 6 are sort of like when an innovation is in its initial concept, if you like. Now that might be facilitated by one of our sort of accelerator programs, for example, led by the innovations team, or it might be working with universities to bring that to TRL level 6, for example. And a lot of that is the focus is on the innovator bringing it up to that stage, and then we get involved a little bit later. So when it's a bit closer to network, but we can offer the technical advice on specific innovations when it gets to sort of level 5, 6, for example. So then once we've passed that stage, we're at a point where we could actually put it on the network. And then the way that we do that is by departing from an already published specification, say for asphalt on the network. So we in our team would grant the departure for that use, and the process is actually using a risk-based approach, and this is an acronym for safe as reasonably practicable, or safe as is reasonably practicable. So that's the sort of we want to get it as safe as possible before it even touches the network. So it's a risk-based approach. So by that stage, if you've got your departure, then it could be laid on the network in a trial site, and then it would be subject to the future monitoring after that. But something that I'll come on to is that we often get stuck at this stage. So we've got a trial material on the network, but we getting to the next stage where we actually write it into a specification for routine use is the tricky part. And a lot of that's driven by we can see it on the network, we can see it performing, but we don't really know how long it's going to last. And that's one of the big problems that we have with any pavement material, because even a surface course, for example, is expected to last 12 years, maybe more. So, you know, it's okay now, but what about in the future? And we often, that's a, you know, a research question that we often remains unanswered, but perhaps I'll talk about that a bit more later. So those are the general approaches to innovation, progressing through the technological readiness levels. Now, what about opportunities to reduce emissions in road materials, pavement materials, and specifically asphalt, which is by far the most predominant material that we use on the network. And the remit for that falls squarely with us in the pavements team. So we've done quite a lot of life cycle assessment, carbon footprinting. Here's one example of a carbon footprint that follows the first 5 stages of the standard framework for life cycle assessment. So the EN 15804 standard. So what we did is run, this is for one mixture, so a thin surface course mixture. The clause in the specification is 942, and and you can either use a straight run bitumen for that product or a polymer modified. So for the polymer modified, it would be slightly different numbers, but not too different. But anyway, you can get an idea of where the emissions arise in production of that material and laying it on the network. And you can see that the big hitters are the raw materials that go in, and then the manufacturing of the asphalt material in an asphalt plant. And obviously that has an input of heat because it's a hot material when it's laid, and a lot of the fuel use around the plant contributes to that quite high percentage there. And then on the raw material side, well, aggregates aren't, you know, relatively, they aren't a big contributor to this figure of 21 kilograms of CO2 per ton. It's the bitumen that's the big hitter there, obviously being a crude oil derivative. So where are the opportunities? Well, they're in the production and they're in the material stage. We're also addressing these smaller portions. The transport is largely taken care of by separate initiatives to sort of change the power trains on HGVs, etc. Some of these installation, well, fuel substitutions on site away from diesel to run the pavers and the rollers on alternative fuels. So yeah, they're smaller contributors, but they're also part of the, you know, they're not being ignored, for example. So yeah, so that was one carbon footprint. There's obviously a carbon footprint for other materials. The one that we just looked at was the clause 942 down in the bottom right here. Sorry, it was actually the one in the purple box, so straight run bitumen. And you can see the overall contribution to that on the network of all the asphalt types that we put down. The others are polymer modified, thin surface coarse, clause 929, where that's used for the structural layers below the surface. And then hot rolled asphalt is a further surface course option, but it only contributes a relatively small amount. So yes, this was all part of the road mapping exercise. So if you've looked up that publication, the asphalt roadmap, you'd see this exercise in there. And this is all about us getting a handle on where the emissions come from and the contribution that they make to the network overall. So what I'm really trying to say with these three slides is we know where the emissions are coming from. What can we do to bring these big proportions down? And that's really the focus of our efforts. And taking a step back, these sort of turquoise bars, the plant contributions to the mixture, the fuel use at the asphalt plants, where they're like the supply chain has to make that decision to switch fuels there. We can only influence that by setting targets on you know, overall carbon footprints for asphalt, but where we can really make a difference is in trying to find solutions for the raw material inputs and facilitating new materials that could be used there, which have lower emissions. So further ideas for opportunities of where we can make a difference. Well, talked about the fuel switching at the asphalt plant. We could reduce that requirement for fuel a little bit by mixing the asphalt at lower temperatures. And we've brought in warm mix large proportions on the network, and that is ever increasing. What else can we do? Well, we can make more use of recycled asphalt. It's fully recyclable, so the aim is to try and get higher proportions of recycled material in. Transport emissions I've touched on. The big hitter, the embodied carbon of bitumen, and you'll see from the case studies we've made quite a focus on trying to reduce that by substituting the crude product with other things, optimizing transport in haulage, construction plant emissions, looking at things like switching away from diesel on the sites, and a small but not insignificant contribution is actually trying to reduce the moisture content of the materials that go into the asphalt plant. Obviously, you have to drive that moisture off as steam to get to the asphalt product. So, getting rid of that water is worthwhile. So all of these things have been put into a waterfall of where we might get to by 2040. We're not going to, at the moment, we're not getting to net zero, but we're hoping that further innovations will come along to fill that gap. Things that we focus on up until 2030, well, the warm mix, the recycled content, better asset management decisions such as preventative maintenance and using longer life materials. And then beyond 2030, well, we'll hopefully see the industry switching fuels at plants and a fuller adoption of what we call biobinders instead of the bitumen products that are used for asphalt at the moment. So it would be either a full or partial substitution to what we call biobinders, and I've got lots more detail on that in a bit. So yeah, so from the carbon footprinting exercise, we were able to put a trajectory of emissions reductions. If we bring everything on stream, we'll get to a point, and there's still potential for more. I think our target is to get below 10% of the emissions, and the rest we might have the option to offset at the end, but that's an option of last resort, for example. Okay, so just to recap, where have I got to so far? Talked about the net zero highways plans and the detailed plans for the materials, the key materials, so concrete, steel and asphalt. I've given you a few screenshots of what was in those roadmaps so far. What I'm going to talk about next is these two boxes. So the actual future asphalt net zero program. So we're looking at specific innovations, trialing them on the network, and lots of different technologies, trying to work out which is best. We also had a net zero concept scheme where we threw everything at one scheme to see how far we could go relative to the 2021 baseline. And we managed to achieve 70% reductions in emissions on one site that was laid at the end of last year. So that's kind of where we got to, and I'll give you more detail on both of those shortly. And then what are we doing beyond this? Well, the aim is to update the specifications to include these innovations once we've proven them enough, so that they just become routine use. Okay, so on to the specifics. So case studies. I'm going to talk about two in some detail, but this is just to give you an idea of some of the ones that we've got on the network at the moment. So we've got a couple of biobinder trials. There's one up in Cumbria and one down in the southwest. I'll go into those in more detail, specifically the A30 scheme that was down near Exeter. Longer life binders, so trying to basically keep materials in the pavement for longer, particularly the surface course, giving it extra life. There are some fairly innovative products around longer life polymer modified bitumens that could enable us to do that. So we've got a few sites that have laid those types of materials for future monitoring. And then the other innovation that we've looked at in quite a lot of detail is including more recycled content in surface course materials on the network. So going up to 50% recycled content, whereas the standard at the moment is between about 10 and 20%. So trying to encourage a lot more recycling, and we're really trying to assess whether that gives us the durability that we need in those materials, having included the recycled content. So there's a few things that are on the network. Right, so I'm going to talk about biobinders specifically. So those that we used on the A30 trial in particular. So biobinders are about substituting out some of the crude derived bitumen, and can that gap be filled by another product? And we think it can, and those are bio-derived components. So effectively plants that have grown in their lifetime, they've taken up carbon dioxide that's locked into the structure of the plant or the biomaterial. That's harvested and then put into the pavement as these oils or more solid components, replacing some of the bitumen, and then it's locked into the pavement structure, so that carbon dioxide is not going to be released as it would do if the plant just broke down organically and returned to soil, for example. So we're actually taking the plant, locking it into the pavement, that locks in the carbon as well. So it's a type of sequestration, if you like. So yeah, we replace a fraction of the bituminous binder, and some of the examples that we've looked at are lignin, timber oils, even microalgae and waste vegetable oils. So, and the ones that I'm going to talk about are proprietary, so I won't name the actual names, but you'll get a good idea of how they perform going forwards. Yeah, that's just a few more examples of proposed bio binders. So wood sources, pig manure, waste cooking oil. Some of the more promising ones are crude tall oil derivatives from, I think that's from pine trees, but that's the huge range of different options that we've got there. And it's not brand new sort of research. This has been looked at in big research consortia led by Europe, for example, over the past decade or so. There's just a summary of a few projects that have explored this concept thus far, sort of giving us a base to work off in our own trials, for example. So yeah, a few big projects there that have looked at this concept already. Okay, so I'll go into detail on one. I've got two case studies, and this was the first one that we looked at biobinders in a lot of detail and actually put it into the surface course on the network, which you can see in the image up in the top right there. So what did we do? So we took our most commonly used thin surface core system, and we trialed two products, a shell product and a NENES product. There's not that many bitumen suppliers in the UK. There's about 3 or 4. So 2 of the big hitters have got these types of products already. So we put them into a surface course, and we put a control section of more conventional material for direct comparison of the performance of the novel pavement against going forwards. And this was done through a departure from standard. And this was the first one that we put onto the strategic road network in England. You can see where that is. As I mentioned, it's down near Exeter on the A30. Specific references to the location there. And this involved quite a lot of collaboration. So ourselves working with the 2 bitumen suppliers, Heidelberg Materials, they were the contractor and the material producer. And then Nottingham University did a lot of the subsequent testing of the asphalt materials, and our consultants helping us out were at Atkins Realis for this, for these trials. So, and it went through a number of steps in about 3 months. So designing the trial, the departure, installing the material and sampling it subsequently for further testing. The slide doesn't really show much, but it's actually a comparison of the novel surface against the conventional one. One's a bit in higher exposure, but they look quite similar, so no concerns there. And then, yeah, probably not too interested in this, but it was just what temperatures were they installed at, and one important aspect is what textures they achieved on site, where they're all very similar ranges, and the texture is related to the skidding resistance. So that's why those sorts of things have to be in the same sort of ballpark. Obviously, there's specific limits for them within the specification. So that was installed, and this is just to give you an idea of all the monitoring that we undertake on such a novel material. So there's testing at the laboratory, there's testing at the asphalt plant, and then we also conduct field monitoring of the sections that have been installed by our routine surveys that already run across the network. So yeah, so testing, so we've got a conventional binder, we've got the novel binder, and then we would put it through this suite of tests, scale 1. So that's just the binder versus the binder, not in the asphalt. And then we put the binder in the asphalt mixture and test that through another series of tests, looking at different properties of that asphalt material. And then the final step is the field monitoring, whether it's on the network. We run our survey vehicles and check its performance annually. So those are the types of tests that happen. Yeah, this is just comparing the 3 binders. So the control conventional binder, the crude derived binder versus the biobinder, the 2 different biobinders. You probably can't get much from this, but this is a suite of tests that binders are put through as part of a European norm. So we test all those properties, and you can see that they're very similar despite the biocomponents being in them. And then some of the tests on the asphalt mixture, well, we test the compactability of the material. You can see the control versus the biobinders here. No real concerns here. One compacts a bit better, but all in the same sort of ballpark. So the idea behind these tests is that the voids in the asphalt are within a specific range, and it basically should be dense enough to withstand future trafficking. So that's the idea behind this particular test. And then we'd also subject the asphalt mixture to, for example, wheel tracking tests, which is basically a test that tests the susceptibility of the material to rutting. So when vehicles are driving across the asphalt, is there going to be a dip created in the wheel tracks? What's the susceptibility of the material to that happening? So there are laboratory tests that approximate that happening by applying a load across the material and running it back and forth. And then after a certain number of passes, you get to measure the rut depth and see whether that's satisfactory or not. But they both were capable of being installed in very heavily stressed sites. So that was a good outcome. And then one of the other tests is all about the tensile strength of the material. And that's actually tested before and after being put in water for a period of time. So what's the relative strength of the material before and after it's been submerged in water for a certain amount of time? And then you get a ratio of the tensile strength as a result of that. And we look for more than 70%, where it's actually 80% for warm mixtures that are more in routine use now. And you can see that the strength ratio was satisfactory or very satisfactory on that front as well. And then finally, for that trial site, we did a carbon footprint calculation. This is all following the same standard approach that we produced the pie charts from, that I showed you right at the beginning of the presentation. So how much carbon did we save relative to a normal thin surface course? About 22% by making this binder substitution, and that was the substitution was between about 10 and 20% of the crude product. So there's potential to substitute more, but that was a good level to explore to start with. And yeah, the carbon footprint was brought down by close to a quarter by the initial attempt of us to use this type of material and keep everything else the same, which is quite critical in a trial. So so that was the first case study. That was the first initiative under the Future Asphalt surface course project. And it was exploring one particular innovation, which was biobinders. But we've also got a long list, if you like, of other innovations to test. And in the past year, we've actually taken forward trials relating to the longer life binder products, graphene additives, higher reclaimed asphalt, and the use of what we call biorejuvenators, which actually facilitate higher recycled contents in asphalt by restoring some of the aged binder properties to something that's less aged and therefore likely to perform better in a fresh asphalt course, despite the recycled content being in there. So we're following a staged process of filtering the innovations, the laboratory testing, the life cycle assessment, and how on earth do we get these into the specifications, which is about a year or two down the line. Okay, and then a bit less detail on the second case study, but this was the one where we threw all of the innovations we could think of and to see how far we could go and install that on the network. So this one was up near Leeds, somewhere near Bramham, but on the A64, completed at the end of last year. And by doing everything we could, working with Tarmac, we managed to get a 70% reduction in emissions relative to the baseline for this particular site. And as I said, we threw everything we could at it at the moment. So the materials that were used on this site, where they were warm mixed with a biobinder included. And we also increased the recycled content up to about 40% here, and also put the long life bitumen products in at the same time. So you can see that if we're going to get anywhere near the 2040 net zero target, we have to start stacking all these innovations together and seeing how they work together. And but this particular surface course has got all these different things in it together, so we can hopefully see how they all interact and whether they're compatible. So those were the material innovations. And then the equipment, well, the diesel was swapped out for either electricity in the rollers that we used on site, or hydrogenated vegetable oil, so swapping the diesel for that. So that made a small a contribution. In terms of the working methods, well, they were facilitated by actually closing the site and not trying to do resurfacing just at overnight intervals. So by having full control over the site, we're able to implement different paving technologies to, for example, eliminate joints in the surface. And joints are a source of weakness in the pavement. So we're able to, what they call lay pavers in echelon. So one paver against another. So the joint was actually not present. There was no need for a joint. And that was facilitated by having possession of the site for a weekend to try these different things. And also what that paving operation allowed was actually to focus on obtaining a smoother surface. And there's some benefits in doing that specifically as well. So they actually contribute to in-surface benefits of the pavement if it's laid smoother. So by using the echelon paving method, smoother surface, and that was verified by what we call the International Roughness Index. So before the works, the pavement was had bumps in it that contributed to a roughness of 2.1 meters per kilometer. So that was reduced to 1.4 after the works. Now, if you have a vehicle traversing that surface is gonna, with a less bumpy ride, it's actually gonna have improved fuel consumption, and we're able to basically work that out, what the saving would be in the year after resurfacing, using a particular model for smoothness and how that's attributed to fuel consumption. So that was one benefit from laying the pavement smoother. And there's also some evidence that suggests that pavement surfaces that are installed smoother last longer. It's quite an old study, but it's kind of logical as well that laying it smoother, you get less dynamic loading across the pavement, and therefore the pavement structure will remain integral for longer, basically. So that was a potential finding as well. Okay, and then I'm coming quite near to the end now. So challenges in implementing and scaling low carbon opportunities. Well, as I alluded to with the TRL levels before, we get to sort of level 7, we get a material installed on a site on the network, which gets us to TRL 7. And then quite often what happens is it stays there for a long time, and it doesn't become routinely specified. And that's because of our concerns about the long-term durability of the product. So we can look at it after it's been installed. Okay, it looks all right, but what about in 10 or 12 years' time? How is it going to perform? So, I mean, partly we have to take some risks here, but obviously those risks are quite high profile. If the material fails on the network, then there's lots of bad publicity for us. So we have to sort of mitigate that to a certain extent. Basically, we just have to be confident enough in the material to allow it to be used routinely. And we sort of encountered this with a couple of innovations that have been around for a bit longer. So warm mix asphalt, well, we've gone to default use of that on the network, but that was after we'd granted about 200 departures for its use since 2015. So you can see how long it took to actually routinely specify warm mix. The same for increasing the recycled content in asphalt. So from below 10% to up to 20. Took a lot of time to build the confidence in doing that. But we've got there eventually. But we sort of realized that we can't take that long for these new innovations if we're going to get to net zero in 2040. So, but we also need to take into account that license agreement, which is about whole life consideration of the asset and how frequently you have to maintain it. So the big question is, how do we adopt new material technologies sooner without compromising on the durability? Do we just have enough confidence in early life performance after, say, 1 or 2 years and say that's okay? Could we make better use of probabilistic modeling? That's certainly an approach that's been tried a little bit with some published papers around that. What we don't really have is the capability to do accelerated testing in this country. Some countries use that a bit more, but there's using big, expensive bits of equipment. For example, in Germany, they've got accelerated pavement testing facilities, but we don't have them over here. The other final point is that the using the departure system allows us to put a lot more conditions on use of the material, and if that's taken away, we can no longer do all that suite of testing on every material. It's kind of like that's taken away from us. We just have to revert back to the harmonized European standards and the testing regime that they prescribe, which is less intense as what we would do for a departure. So that in itself presents us with a bit of a problem. So solutions around this would be awesome, but you know, it's a perpetual question in pavement engineering. about how long things are going to last. Okay, so final slide, just to conclude, what have we covered? Well, opportunities to reduce emissions and improve sustainability, they're outlined in our strategies, so have a look at those. And there's guidance that sits alongside them to assist the actual progression of innovations through the technological readiness levels. So hopefully that's helpful. The latest innovations that we're looking at target all aspects of the life cycle of a road material in order to reduce carbon. So you could look at any of those life cycle stages. You know, we need savings across the board. And obviously I highlighted the big hitters in the life cycle for asphalt at the beginning. I've given you an insight into two of many potential case studies where we've demonstrated successful integration of low carbon solutions. The ones we looked at today were the A30, the first biobinder trial on the network, and then the A64, where we tried to get as close to net zero as possible and got to about 70% carbon reductions. And then finally, the biggest challenges that we have in implementing and scaling low carbon materials are the problems associated to how do you predict how long that material is going to last on the network and not need replacing more frequently than the ones that we use already. So that's the end. I'm happy to answer any questions.
Thank you, Matt, for the wonderful presentation. We have a few questions in the chat. And the first question, which I also had and you also mentioned about, is about the longevity of the low carbon materials. You mentioned that this is a research question that remains unanswered. So the question that comes from Phil, how long will these new materials last? And thus, could they make transport infrastructure less resilient?
Yes, there's always the risk that they might last a little bit less. I think, and on to the resilience question, I mean, yes, effectively that would make the network less resilient. So yes, there's a risk that they will be less durable, and that is the big question, probably the biggest question about when we get to the point when we're confident enough that the materials will perform as good as those on the network already. And yeah, the suite of testing that we saw is extensive, and that's aimed to mitigate that risk as far as possible. So I don't know if I've really answered the question, but that is the big question that we try to answer every day, really. How long is it going to last on the network?
I have, I was also thinking about that. And I was thinking whether we should specify that along with EPDs, the commercial products should also tell some indication of how long they will last under some circumstances. Should we mandate such kind of thing to make sure that we are trialing the right products?
Yeah, that would be a good position to get to, but I don't think, if we can't predict the life, the material producers can't either. The only way that we can try and mitigate it to some extent is by having warranties on the materials, but those material warranties are obviously affected by the conditions that you put the material down onto the network. So a contractor could always come back with, well, we laid that on a poor substrate because you didn't replace the layer beneath at the same time as putting the surface on. therefore the warranty is null and void. So we encounter that problem as well. But the thin surface course materials have 5-year warranty, so it kind of at least mitigates any early life failure in them. But we don't ask for sort of the whole lifetime to be in a warranty. So yeah, it's a tricky question.
Okay, we have the second question in the chat. What are the comparative carbon emissions from biobinder manufacture compared to normal bitumen?
Well, that's where I think a lot of the savings come from, because obviously bitumen's a crude derived product, so it's got all the sort of upstream impacts of oil extraction associated with it. So the drilling, the refining to get to the product, whereas with a bio-based or plant-based material, the refining element is less onerous, I think. And obviously it grew somewhere in a field, so the production's less impactful as well. So I think, and also some of the emphasis on use of biomaterials is to use those byproducts of plants that aren't really used in other industries or for food production, for example. So the emphasis is to try and use the byproducts, for example, the lignin, and find a use for that within the pavement. So all of the production has actually taken place already to get to the primary product, and then you've got a byproduct that you could use in a road pavement. So a lot of the impacts are less from that point of view as well, because you've been focusing on producing the food rather than the byproduct there. So
yeah, in relation to the question, we have another question. Did you find much difference in durability, laying, life, monetary cost, etc., between biobinders and bitumen?
Yeah, so the bio bitumen products are slightly more expensive at the moment, but I think that's partly because they're new as well. And if we were to scale up their use, I think they would the cost would come down basically. For example, the shell product that we looked at is produced in Rotterdam. It's not produced in the UK at the moment. But if the demand was enough from us, I think we buy about 23% of all the asphalt in England. So if we made that switch to using biobinders routinely, then the demand would be there. The carbon emissions would come down because they would produce them more in this country, and probably the cost would come down as well. So yes, so the answer is they're a bit more expensive at the moment, but we would anticipate that would sort of come down over time. Yeah.
Did you find any changes in the durability or life?
Not so far. Not so far. Obviously, the aim of putting trial sites on the network is to actually subject them to regular traffic, and then we sort of follow those, monitor those sites with surveys over time. In the short time that they've been put down, they're performing the same as conventional materials, but it goes back to the question that I've referred to quite a lot. Yeah, how long is it before some deterioration shows up, and how many years do we wait before we actually say that it's acceptable? So
yeah, I have the next question related to that. You mentioned about trialing and including it as a departure from standards, right? How long will you be monitoring the performance before including it in the main work?
okay, so our timeline is to try and introduce them into the standards next year. So 26, 27. So after that time, we would have had 3 or 4 years on the network of some of these materials. Yeah.
So ideally, it will be like for more than 5 years of monitoring.
Ideally, it would be, but we realise that we need to move quicker. So somewhere along the line, someone's going to have to make a decision based on the risks. Do we just go with this after a year or two, or do we wait longer? And I think we're trending towards taking a few more risks at the moment. So after 2-3 years, we'll probably make a decision on whether to use them quite routinely.
And I have a question related to the trial as well. Was there any change in design or thickness when you used a bio-based bitumen, or is it the same design but you just changed the material?
Yeah, so the thicknesses didn't change; they were the same. So what a lot of it was about was trying to establish whether the biobinders have the same performance levels as a conventional bitumen, given that everything else was the same. So did we change the mix design? Not really in terms of the gradation of the aggregates. That would have been the same. I think I'm pretty sure that the actual binder component was very similar as well. I don't think that was actually changed. It was the same percentage bitumen, if you like. So all things being equal is what I'm trying to say, is that we're trying to test their equivalents. Yeah.
Okay, we have one last question from the chat. How do we get access to the low carbon opportunities register?
Okay, I'm more than happy to share the link afterwards, but there's a link. You fill in a form and you'll be granted access. So that's no problem. I just have to find that after the call and share it with you.
Okay, we have one more question that came up. How is it decided how much risk can be taken with the low carbon materials?
Yeah, that's a good question. That's a hard question to answer as well. What we can just prove them so far, and then really it's up to, yeah, I don't really know how to answer the question. We have to take a bit more risk if we're going to get to 20 net zero in 2040. But we can use the slide that had all the testing that we've undertaken. You can see that it's pretty extensive, and if we're getting equivalent performance across all those tests, particularly the in-service sort of monitoring for a couple of years, then we're pretty confident. There's not much more we can do. So someone higher up in the company just has to say that we're going to make the switch, and that's what we did with warm mix in the end, and it's not caused us any problems. So we'll probably go the same way. Yeah.
Before binding up the chat questions, I would like to ask if anyone has any question. Please unmute yourself and ask the question. I think, okay. Thank you very much, Matt, for being with us and answering our questions. It was truly enlightening to see how you are also thinking about the longevity of the materials and not just focusing on the embodied carbon. So this is one of the main questions we are trying to answer as a part of DARE, that how to do the selection of materials. So this was really interesting for us, and I am sure that it would have been interesting for all the others who participated. And thank you so much for your time and being with us.
Okay, thanks. It's a pleasure.